welcome everyone to our webinar SeNSES, a sensor network for South East Scotland. Today we are joined by Chapple and Tommy Lawson. Simon is the Head of Data Technology in the Information Systems Group at the University of Edinburgh. Under Simon's leadership, the IoT Research and Innovation Service is establishing a regional IoT sensor network covering the whole southeast of Scotland, which will be discussed in today's webinar. Tommy is an experienced engineer, learning and assistive technologist, teacher and school manager that spent 40 years working in the nursery, primary, special and secondary education. In today's webinar, Simon and Tommy will discuss the £10 million government capital funded IoT sensor network the University of Edinburgh is building across the southeast of Scotland. As always, there'll be a chance to ask questions at the end of the presentation, so at any time, please submit these in the Q&A option at the bottom of your screen. I will then ask these on your behalf later on. Thank you for logging in, and I'll now hand over to Simon and Tommy.
Thank you very much. Welcome everybody. Thank you for having us along today. So my name is Simon Chapple, and Tommy, my colleagues, with us as well. So I'll start by giving you a bit of background on the project as a whole. So SeNSES, which is what we call the sensor network for South East Scotland that we're building over a number of years, arises from funding that we have through a city region deal for South East Scotland. So city region deals are throughout the UK. This one was established back in 2018. And it's around about a 1.3 billion worth of investment over a number of years. It actually runs, the programme as a whole runs over a period of 15 years. It involves the 6 local authorities in South East Scotland. So that's all of the Lothians, including the City of Edinburgh Council, as well as Fife to the north and Scottish Borders to the south. Now, as part of that, the university is actually a lead principal partner in that particular city region deal. So it's the first of the university-led city region deals. And as part of that, it receiving around about 110 million in capital funding from both Scottish Government and UK Government. And that money goes into the establishment of what you can see in the centre of the wheel diagram here, to the EIDF, which is the Edinburgh International Data Facility. And within that, there are a small number of sub-projects, and we're one of the sub-projects, which is the IoT Research and Innovation Service. And we receive just under about 10 million worth of capital to spend over a period of 10 years, starting back in 2018, ostensibly on the establishment of a regional sensor network. So that's where our beginnings started. Now, the purpose of the program as a whole is to stimulate economic activity, as well as to improve knowledge capabilities amongst the population through education, through community engagement, those kinds of things. There's a lot of infrastructure aspects to a city region deal as well, which largely the local authorities themselves manage that aspect of the program. In the context of the university and the data-driven innovation program, we have 5 key hubs, which are the Usher Institute, which deals with kind of health and social care aspects of things, the Bayes Centre, which focuses on informatics and AI development. We have the National Robotarium, and we also have Easterbush, which deals more with the veterinary side and farming side of things. And then we have the Edinburgh Futures Institute, which deals with a lot of the social change associated with future technology. And the key thing about the program is it delivers on 5 key outputs, which are known under the TRADE acronym. So that's talent, so that's the training and knowledge capability, particularly around being able to handle data, research, adoption, data, and entrepreneurship, which I think are fairly understandable in their own right. So we started back in 2015 testing out and evaluating particular technology, low power, wide area networking, and using that to relay data from sensors. And this is based on something called LoRaWAN. LoRaWAN is now very well adopted globally. I think a lot of people have heard of it by now. And you know, there's a huge amount of uptake globally in that technology. When we started in 2015, it was still quite nascent in terms of its development, and we installed gateways across the university estate. So University of Edinburgh has 5 campuses essentially, one very much in the centre of town, another one far to the south, the Easter Bush campus, and then we have other campuses spread throughout the geography of Edinburgh itself. Edinburgh is an interesting place terrain-wise. It has a lot of topography, so we have some big hilly bits in us, so there's cavernous bits, so understanding how the technology works, particularly in this kind of urban context, was really interesting. Each of the blue circles you can see centered on that is one of our gateways deployed to a building, a university building. There's about a 5 kilometer radius. You can see that we have quite long distance capabilities, particularly under line of sight, which is a key thing. But within the kind of urban context, you're talking 1 to possibly 5 kilometers, just depending on exactly what happens in terms of the radio transmissions and the level of clutter in between transmitter and receiver. But the key thing is it's low power technology. So these are battery powered devices, which can have small batteries in them, that can last up to 10 years typically. And the other key aspects of technology is its low bandwidth. So it achieves its long range, which is essentially what the lower part is, through the type of radio modulation that it does on the signal. And that's the key part of the technology itself. It runs in the UK and the EU in 868 megahertz range, which is part of the ISM band, so it's free radio spectrum. But there are specific requirements for anybody operating in free radio spectrum, and in relation to LoRaWAN in the UK and EU, there's a maximum amount of transmission time a device can have on the network. And this is around about 1%. So you maybe get 60 seconds in an hour in order to be able to do transmission. And so this is suited towards devices which periodically send messages. This is not for streaming. You can't do any streaming with it. The bandwidth is very, very low, but it is very useful for relaying sensor data from devices deployed widely in the environment with a minimum amount of infrastructure. And it's relatively low cost. So the infrastructure investment here is much lower than doing anything with, say, mobile phone technology or something like that. So what we did in the context of the city region deal was we pitched in to actually grow and establish a network across the whole of South East Scotland based on that technology. So over time, between now and essentially 2028, which is the duration the program runs, we'll be establishing gateways for relaying data from SeNSES, and we'll be putting something like 10,000 or more devices out into the environment. And there are some key aspects that we want to develop from this. Capturing a unique environmental data set at a particular resolution and over a long period of time. So this is about real-time data processing. Developing what we call edge of network intelligence. So this is where signal processing actually takes place within the devices which are deployed, rather than lots of data being streamed back to a central location and processing actually being done there. And there are different aspects to environmental sensor data that understanding what the weather's doing is generally useful for all sorts of applications. Now, the key thing is that how we actually make this happen, obviously you've got to be able to deploy things to places, and the way that we're doing this is through our engagement with all of the local schools in South East Scotland. So here you can see basically a map out of all of the primary and secondary schools. There's around about 550 odd schools in South East Scotland. That represents a school roll of around about 130,000 school pupils. So the way that we do this is we deploy gateways to these schools, and we also deploy sensors to these schools, and we co-opt them essentially as a volunteer force to help look after and maintain our network. But the quid pro quo on this, of course, is that they need to get some value out of this. And so the key thing here is that we have a very strong educational element to what we do in terms of deploying this technology and having the school pupils make use of the technology, which is what Tommy is now going to describe in terms of our IoT in schools program.
Okay, thanks very much, Simon. I'm going to cover very quickly what we're doing in schools and why we're doing it. So as Simon mentioned, this is part of the data-driven innovation for South East Scotland, and that sits alongside the Data Education in Schools initiative, which aims to develop data literacy amongst all our young people and feed into the tens of thousands of data professionals that we need in Scotland in the coming years. Next slide, please, Simon. So we have this innovative technology going into the hands of learners. From a technical perspective, the gateways are going into schools, 4G gateways, 4G backhaul for the pilot schools, and now we're working with education authorities to install these gateways onto the LAN. Since the sensors are connected by LoRa, which Simon mentioned, long-range radio, the range over which we can connect back to the gateway makes such a difference to the types of sensor, to the application, to the location that the learners can deploy. So inside and outside of the school environment, and we think quite effectively into the local communities surrounding each school. So we're building a community portal which the learners can access and they can collaborate with each other, school to school within the portal. And there's an interesting offshoot to the project, which I will say a little bit more about in a few minutes. We're creating a virtual town on a virtual island just off the coast of real Scotland. So none of this would be worthwhile doing unless it integrated into the curriculum and there was some educational impact in doing so. Now, I talk about integrating this into the curriculum. Every month along comes another idea of what we want our schools to teach. But for us, the curriculum is stappet full. So it's full to the brim and there's no room for any more. So thankfully, the Scottish curriculum is based on a set of experiences and outcomes across mathematics, languages, science, technologies, social studies, religious and moral, health and well-being, expressive arts. And each school can decide the context of how they will achieve these outcomes. So the content being taught in an inner city school in Glasgow may well be very different to that in a Hebridean island school. And that means that we can integrate much easier into the existing learning and teaching. Rather than adding on to the curriculum, it's replacing some content that's already there with different ways of learning. For example, learning to interpret a graphical visualization of a number of packets of crisps sold in a fictitious shop can now be replaced with graphs that representing real life data coming from around the youngster's own school. And our initial thoughts that we would probably look at dipping fairly closely into numeracy and science, but we've got some very creative teachers out there coming up with great ideas. And at the moment, we're looking to develop interdisciplinary learning projects that teachers can pick up and deliver according to their needs and interests. Our young people are also fired up around the main underpinning themes of climate challenge and sustainability. So that fits in well with our project. Next slide, please, Simon. So the sensor technology going into schools, we've got 35 schools at the moment on the project. Largely indoor environmental monitoring. These little devices top left are about the same size as a central heating thermostat, measuring temperature, humidity, air pressure, CO2, light levels, and presence. Lightweight, they can be stuck to the wall with blue tack or Velcro, and a 5-year to 10-year battery life. Bottom left is the soil moisture and conductivity sensor that we're putting in now. In the middle, there's outdoor environmental sensor, which adds on particulates monitoring. And on the right, something that we're working on just now, a weather station. Next slide, please, Simon. So the sensors go into school and the learners can spend a bit of time learning about the digital technology, or they can cut to the chase and see what data is coming out of the other end. So each sensor sends its sensor readings to the local gateway by LoRa, then over the internet to the cloud-based applications that extract the data and make it available in graphical or tabular form. The technology in the middle is somewhat transparent unless a teacher wants to delve into the detail. And we've developed a series of lessons that learners can use problem solving around some of the entities that will affect their own learning environment. Slide 10, please, Simon. Now, none of this investment into technology into our schools is worthwhile unless there's a significant educational impact, the so what question. Our immediate impression, listening to teachers and learners, is that it is making a difference. Learners are motivated and excited by what they are doing. And as a seasoned teacher of 40 years or so, it takes a lot for me to perk up and think something is actually working well or potentially a game changer. In the last slide, you saw the words, I see, I think, I wonder. And it is the I wonder part that I'm looking for from our learners to demonstrate their understanding and their thirst for new knowledge. One example, my favorite, comes from the week of the Tonga volcano eruption. The girls in this slide and their classmates saw a blip in the pressure readings from the air quality monitor. A number of hours after the explosion, I suggested to them that it might be related to the Tonga eruption. So they set about working out the time difference, the distance around the planet from Tonga to the village of Roslyn. Excuse me. Then they worked out the speed of the pressure wave as it traveled around the planet. We put them in touch with one of our staff, a volcanologist who was actually down in Ecuador studying a volcano at the time. And the youngsters connected through the video conference and presented their findings to that member of staff. And would it be a surprise to you to know that the calculation of the speed of the pressure wave was almost identical to that of the scientists? Their I wonder questions were also fantastic. Does the pressure wave travel the other way around the planet? And what happens when the pressure waves meet? What difference does the weather make to the speed of that pressure wave as it travels around the planet? And is this huge ash cloud going to affect the weather right across the world? Last slide, please, Simon. And finally, while we were twiddling our thumbs in lockdown, we couldn't get into schools. And so something called Datatime was born. It started with the idea of creating a virtual school so that we had some data for the young people to play with. The idea grew, and instead of a school, we created a town called Clydach. Why stop at a town, we said. We therefore created an island and placed it just off the coast of St Andrews in Fife. Now we're currently building up the data set for the island, and we've lots of people, fictitious people, 26 island locations, which include wind farms, hydro farms, retail parks, hospitals, lots more. And we can run scenarios. For example, the first one that we've developed is a thunderstorm. What happens when a thunderstorm hits the island? We've got rain, we've got changes in wind and therefore electricity generation. We've got changes in river depth and flow. We've got more electricity demanded. We've got increase in traffic. We've got increase in emergency calls. And we can play these out with our learners and ask them to problem solve around these events. Next slide, please, Simon.
Okay, thank you very much, Tommy. So I'm just going to kind of finish off the presentation by talking a bit more about the infrastructure that we've deployed to support this network and what we're using it for, and give you some examples of the projects that we've already engaged in. So this is the infrastructure which sits underneath that network. The part on the left, the green bit, is the LoRaWAN physical network itself. So this is the LoRaWAN gateways communicating with edge devices. All of that data feeds back, and the control mechanism, the management mechanism, is all done through an implementation of a LoRaWAN server. And the one that we use is the Things Network, which was the first community edition variant, if you like, of LoRaWAN, trying to encourage community participation and actually standing up a network worldwide, and which has been very successful. They're in many cities globally across South America, Europe, and America itself. So that's what we run. And the data comes into there and is immediately passed on to our data capture mechanism. And for that, we use the Elastic Stack and Kibana is the front-end data visualization component within the Elastic Stack. And that's where people have access to the data. There are other mechanisms that we use for providing real-time access to the data and also taking snapshots of the data and placing them in the broader Edinburgh International Data Facility, where it can be combined with all sorts of other longitudinal data sets and be used for all sorts of different types of applications. Now, one of the key things about having this network set up is we want to develop and deploy edge of network intelligence. So this is using the network for the data capture, using the greater facilities, compute facilities in particular of the Edinburgh International Data Facility, which includes things like the National Supercomputing Service and those kinds of components, and brand new dedicated cluster computing with GPUs for accelerated machine learning. And then what we do is compile, or the principle is that we will take those models, compress them to some extent and compile them and deploy them out to our network of much more simpler sensors. So when we first started this was an idea and it wasn't a reality. It is now very much a reality, and you'll find that there are even commercial companies setting up and using this same kind of technology mix. On the left there, you can see an example of a new product line that's just been launched by Seed, a Chinese company, into the world of IoT, which is using this same kind of structure. So using LoRaWAN, having these compressed, very small power kind of machine learning engines, classifiers deployed in something called TinyML. So it's all very workable right now. So our plan going forward over the next 5-6 years is to focus on certain thematic areas, and I've talked about them already really. So the environment, biodiversity, and then in some sense a bit of a catch-all, sustainability. So everything that we're interested in, both in terms of the applications that we're building, as well as the way that we actually build them, is geared towards sustainability. We have a lot of use of IoT and sensor technology in the context of developing smart campus and doing operational decision-making within the university itself. We also have a particular focus around biodiversity monitoring and digital biodiversity monitoring. So this is really taking some of the biodiversity monitoring that's done in a kind of deploy a device and then pick it up a month later and then look at all the recordings it's made, and actually turning that into a real-time type service. And we'll do that for vocalizing parts of the animal kingdom, but it can also extend to insects. And then on the environment side, we've got lots of projects in play which cover off a range of different things, very particularly interested in air quality monitoring and pollution, both indoor and outdoor. And indoor has become much more kind of prescient in terms of COVID and the spread of virus in an indoor situation. And in fact, the monitors that Tommy was talking about, which are going into the schools right now, are CO2 monitors themselves. That wasn't part of our plan. Our plans were set well before that. We were mainly thinking about concentration levels in rooms where there's lack of oxygen. But we're also working around things like issues to do with water flow and things about water pollution in the area of southeast Scotland. And then there are other types of projects which are looking at energy use and comparing that with the actual utilization of space in buildings and energy recovery. And also we have a big aspect to do around with smart or sustainable tourism. So here's an example of data that's captured using a personal air quality monitoring. This is actually from Helsinki University, and I've actually got a new version, latest version of that particular device here in my hand just now. I'm showing you. That enables us to do particulate monitoring. It also has a number of other types of sensors on it as well. It'll do volatile organic compounds and those kinds of things. So it's possible for us to pick up the real-time data, and we're looking at applications which are looking at trying to highlight routes for people who are affected, particularly by air-based pollution, so that they can navigate the city environment and choose those routes which are going to lead to less irritation of their particular condition, whether that's asthma or some other kind of condition that they might have. We've done projects in terms of biodiversity monitoring in the kind of urban park context. So here's an example of what we call a smart notice board. It's got all various different bits and pieces in it, but you can see there's an ultrasonic microphone. This is all low power stuff. So doing bat detection, just using pi zeros and those kinds of things, very low power budget required for this. We just stick a solar panel on top of the notice board. It will basically keep going all year round with a decent battery on it. And we can monitor this system and keep an eye on it and get real-time data back around that type of detection. Also used for understanding some activity aspects of people using around it as well. And the final project I'll just highlight here is we've been doing work with East Lothian Council to do beach car park occupancy. This is about sustainable tourism. Lots of issues with, particularly during COVID, it became very much relevant because obviously people are not holidaying abroad, they're doing staycations, is just what level of occupancy of these kind of beach areas happens, and we're doing that through car park monitoring. It helps give people information back. So what you can see just down on in the middle there, left of middle, is a view of an app in a mobile phone, which tells people how busy each of these kind of beach car parks is, so they can choose where to go based on that. But certainly the locals are seeing a lot of impact from over parking in and around those particular areas. And I suspect our time is just coming to an end. So one thing I was just quickly going to do, if I can stop sharing that screen and then share a different screen. I thought I would give you a live view of the system, so hopefully that's coming through in a second. There we go. So this is a view in Cabana. It's showing you all of the schools. So all of those circles are schools. The ones that are kind of filled in a purple are the ones that have active sensors on our system at the moment. We can click on one of these and that just takes us to the dashboard, which gives us all the sensors. So this is Roslin Primary School, which is one of our lead early adopter schools. They have a lot of internal sensors in here. You can see we've got a dozen internal CO2 sensors, and they also have an external air quality monitoring sensor, and they also have a couple of soil sensors as well. So clicking on these allows us to pick up and see in real time what's been happening with the air quality monitoring outside, so we can see the particulates level, temperature, humidity, that kind of thing. And then indoors we can pick individual sensors, and we can see that actually this morning you can already see that this room is quite well occupied as the pupils have been attending class in this particular room. And that's where I shall stop.
Perfect, thank you guys for that. We do have a few questions, so I'll just work our way through them. The first one is, are you planning to include CO2 and PM monitors or extend it to other air pollutants, e.g. NO2?
So certainly we're not, I mean, over time, there will be various different sensors which will be placed into the network. They will be driven by projects mostly that spin up and make use. So we have had discussions previously about measuring more pollution gases, but what we would look for is a project to derive that specifically to bring those sensors into the network. So whilst we've had discussion about it, we don't have one on the immediate horizon to do that part, but there's a lot of interest in particulates in particular, he says, and certainly in relation to schools and pupils arriving at school and being dropped off, being collected from school, and the issues around vehicle pollution around that. That's certainly one of them. And we're in some early discussions with some projects which are interested in general in air quality monitoring, a couple of projects coming from the University of Edinburgh on that particular topic. So we expect to deploy AQM monitors in the near future in the city of Edinburgh anyway.
Great. Do you anticipate the devices you're using being available to environmental scientists to be deployed as part of their own projects?
Yes, absolutely. So another thing to say is that all the data that we're collecting, we hope that the broader academic community will be able to make use of as well. So all the data that we're collecting for all the projects, we basically start off with, if we're going to support your project, then you need to make sure that the data can be used by others and not just by the context of the project that you're running. It's a bit different for some of the commercial projects, obviously, that come on and use the network. But in general, absolutely. And we're trying to set up the mechanism that allows us to support projects in kind by deploying sensors into our network and have that component taken out of the costs of that particular project. And then that's something we're working on at the moment.
Great. Someone is asking, what is the accuracy of the personal AQM?
The accuracy. So it's pretty accurate. The particular monitors that I was showing here, this is a MegaSense 1. It comes from the University of Helsinki. You can go and look up and see the papers associated with the HOPE project from Helsinki and all the validation associated with these particular personal air quality monitoring sensors. I don't know the figures off the top of my head, but I know that they've done a lot of work validating the units that they've actually created.
Great. How will the collaboration and how will the calibration and maintenance for over 10,000 sensors be carried out?
That's a very good question. So I mean, obviously sensors that we get arrive to us calibrated. We do look at deploying multiple sensors in close proximity with one another. So something that enables us to see is whether or not a sensor is kind of reading off the scale. So if an individual sensor goes wrong, but I would say that that's an active area of research in terms of these kind of deployment at scale of sensors and what mechanisms do you use to track their accuracy over time. Obviously individual sensors based on, you know, we're not really focusing on gas chemistry type sensors at the moment because those are ones that typically have relatively short lifetimes, particularly the very accurate ones associated with them. So that's something that we'll come to in the future. There's a lot of low hanging fruit for us in terms of sensing to do before we kind of get into those. But yes, I think the key to that is really to take multiple readings from many sensors and then do some kind of overall analysis which tries to determine whether or not individual sensors are misbehaving. There are also different types of sensors that we can deploy together so that the different readings that we get from different types of sensors, again, is something that could be used to sort of intervalidate or cross-validate such things over time. But if you have a project and an idea about how to do that, then come and talk to us and we'll see what we can do to help you.
Great. And the final question here is, given the topography constraints, would this approach work to expand the IoT environment monitoring further north in Scotland?
Yeah, definitely. I mean, we've got quite a lot of experience now of topographical issues, and nature gets in the way as well. So leafy environments and the forest canopies and things like that all have their impact on propagation of radio waves. This is sub-gigahertz radio, so it's more, it's less affected by some of the things that higher frequency radio transmission suffers from. And the nature of the modulation on the radio is also really good at working through noisy environments, noisy RF environments. So it's pretty good as technologies go for the money that you have to spend to make it work.
Great. And there was just another question that came in. Do you post-process the AQ data to account for weather conditions? The East Coast is often impacted by HAR, and without heated lines, low-cost sensors are likely to suffer from such high humidity.
Yes, I suppose is the short answer. The longer answer is, again, is relying on lots of information. So the more information you can get from the more different sources and sensors and things, and the better you can understand the impact for an individual sensor. When we do audio-based analysis, we also are recording the environmental conditions at the point that the audio is recorded, because environmental conditions affect propagation of sound waves, those kinds of things. So it's definitely a consideration.
Great. Well, thank you again to yourself and Tommy. That's it from us today. Attendees, thank you for logging in, and I hope you found that beneficial and informative. Thank you again to Simon and Tommy. And to all attendees, thank you for watching. Thank you.
Thank you very much. Bye-bye.
Thank you.